Up next, we will hear from Caleb and Krasoon. Caleb is a former Ph.D. researcher at UT Austin's Nuclear and Applied Robotics Laboratory, where he earned a Master of Science in Robotics before leaving to lead Salem Robotics full-time. Krasoon is a Ph.D. researcher at UT Austin's Nuclear and Applied Robotics Laboratory with a Master's in Robotics. Both here will present a nuclear robotics startup pitch. Please join me in welcoming Caleb and Krasoon.
So my name is Caleb. And I'm Krasoon, and we're the founders of Salem Robotics. So throughout our collective experience in the government nuclear facilities, and most recently through our customer discovery in the commercial nuclear sector, we have seen one problem occur again and again. That is the radiation survey problem. Currently, this is manually done by human workers. This entails tens of handwritten reports taken by these human workers and manually transposed into a digital database. Naturally, this method is subject to radiation dose limits, data inconsistency, human errors, and so on. And most recently, it is exacerbated by the aging nuclear workforce and rising energy demand.
So our insight is that these nuclear facilities, of which we have extensive experience in, as well as from extensive customer discovery, we've discovered that many of them have robots that have the capacity and the potential to perform these surveys autonomously. However, they were purchased for emergency situations. They're practically never used. So right now they're just collecting dust at many of these facilities. What's missing is a nuclear native autonomy software stack that would allow these robots to perform those surveys. And that's where we're coming in. We're providing that bridge between to kind of surpass that tech gap and make these underutilized robots give them the ability to perform these surveys autonomously.
It is the solution that we're offering. Our product has two important elements. One is the navigation component. In the navigation component, we have a user-friendly dashboard where an operator can specify waypoints indicating the boundary of the survey. Basically, based on this, the robot, Boston Dynamics Spot in this case, can go and autonomously execute the trajectory while simultaneously collecting data to generate a compliance-ready report at the end. Another important element that we're offering is robotic manipulation, which is essential for radiation survey tasks, i.e. opening doors, moving things out of the way, and things like that. We're using bleeding edge research here, and we have validated this on an actual robot. You can see some demonstrations on the screen here.
So this is also a very timely problem with a very timely solution. We're kind of riding this wave of several contributing factors all converging at the same time. First and foremost, energy demand not only increasing but accelerating in no small part from this large AI boom, all of the cloud services and server farms. This has kind of been a force that has led to a renaissance within nuclear and the nuclear industry, with a ton of research money pouring into new ventures and also ventures that are reimagining how the business model of nuclear should exist. Robots, also, the maturity within that domain has reached a level where these products and the software associated with these products allow these robots to be actually usable within these domains. And then finally, and most importantly, it's that nuclear workforce that in large part came into these facilities at the end of the Cold War, meaning we're reaching a time now where many of them are aging out and entering retirement age. For example, some statistics show that 62% of that workforce is going to be out and retired within the next decade, all while this specific industry is seeing a renaissance.
Next, let's talk about traction. We are already in the nuclear industry. Caleb and I have over a decade experience in this industry. We have talked to over 5 nuclear commercial plants here in Texas and in multiple states. 2 of them have expressed written interest in working with us, and we visited one of them recently and are in active discussions for scheduling a paid pilot down the road. Another important thing is that there is a high barrier of entry to this particular field, which is security clearances, and both of us have a nuclear equivalent top secret security clearance to our advantage.
So kind of breezing through the business model, it's largely enterprise SaaS company where we would enter under most likely just setup fees or an optional pilot period that would cover that setup fee and then move into an annual subscription within each of these sites. The economics are pretty standard for such enterprise SaaS plays, 70 to 80% gross margins at steady state with a projected target based off of pricing conversations that we're having with these plants right now of about 10 million ARR by the end of the first 5 years. The market sizing, our target market, about 10 to 15% of that SAM, the SAM representing both commercial nuclear in the US as well as DOE facilities, which we have a lot of experience at. DOD facilities, primarily the Navy, decommissioning sites, as well as all these new ventures kind of popping up both for like small modular reactors among other new technologies in nuclear, and then a broader TAM well within the billions when you're considering global nuclear as well as adjacent industries with incredibly similar, almost identical procedures, hazardous chemical, hazardous biological, oil and gas, those industries.
So at the moment, no one is offering what we're offering here. But in terms of competition, what comes closest is the status quo, the human worker. But this approach, of course, is not cost efficient. It's not autonomous. It's not as so scalable, requiring a specific niche nuclear training. Is subject to dose constraints and is not time efficient. There are some vendors that supply sensor solutions or some one-off or teleoperated robotic solutions, but these are very limited in scope and require heavy supervision as well.
So our team, which you're welcome to come and meet with us after this, from a high level, we're two Ph.D. level roboticists who've been working in nuclear for, like Christine said, almost a combined 15 years. Our advisors right now, our business advisor, Jim Nelson, is a serial entrepreneur with a $500 million exit in his past, has worked on many startups. Mitch Pryor, who runs the lab here at UT, the Nuclear and Applied Robotics Lab, as the name would suggest, has a lot of experience bringing robots into hazardous spaces and working with a network throughout the US and abroad.
So in this pre-seed round, we're raising $1 million to complete our first paid pilots here in Texas and to transition from our working prototype to a field-ready product. If you have any questions, we'd love to engage with you. We're going to be around throughout this whole event, and we have our contact information here on the slide. Thank you very much.
Thank you. We also probably have like 30 seconds for questions. 1 minute, okay. So if anyone has questions, we have a very brief questions window.
So you mentioned like SMRs as well as like these much older like legacy facilities, super different scale and size. So your software solution, like can you kind of explain a bit about how it works for both?
Definitely. And surprisingly, although they're different sizes, the same governing NRC regulations are identical for both sizes of facilities, meaning that although the scale of the map will be different, the actual procedures being accomplished in, say, maybe a given room or a given facility the size of like, I don't know, a little bigger than a McDonald's if we're talking about like an SMR facility, is actually going to be incredibly similar, if not identical, to those like the plant that we visited, which was enormous, you know, or facilities at Los Alamos National Lab, which we have extensive experience at, which is almost like a small city. However, the procedures are almost identical. But great question, and there will be differences in how they're accomplished, but probably not gigantic differences.
And not only in the commercial sector, but the procedures are largely identical in the government sector as well when you look at both.
Yeah.
Up next, we have Krishanu, who specializes in trustworthy human-AI interaction with experience building data governance systems at Goldman Sachs. Currently, he's building the next-generation co-working platform to bridge the gap between AI agents and your teammates. Please join me in welcoming Krishanu.
The topic that we are going to discuss today is about a framework to assess AI agents, and we are taking a step towards reaching the uncanny valley of agents and humans. you'll be surprised to know that the word AI agents has existed since 1990s. It was coined first by Russell and Novig, but still today there is like a naming problem. Vendors are constantly bragging about their capabilities. Researchers are using inconsistent terminology, and users, they want to use AI agents. But even if they pay money for some tool, they might not be able to solve their problems. So Gartner came up with the framework in 2025. They basically split the capabilities of this agentic system into different levels, starting from minimal all the way towards advanced. They also grouped these AI systems into three groups, starting with AI assistants, which is nothing but you can say Siri. Then the agentic AI, which is the most prevalent system right now in the industry. And you can think of it as Gemini in your workspace. And the third one is AI agents, which starts at the basic level. But basic is not that basic. A cursor lies in the basic level. So all the way towards AGI, and that has not been achieved yet. So taking a step back, you can see that these lines are blurry. They overlap a lot. But by the definition given by Gartner, they actually do not. There exist like subtle differences, as you can see over there. So the critical thing that we want to take away from this is that capability levels matter. And for an agent, capability levels are the tools it has, the skills it has, maybe the short-term, long-term context that it has access to. Maybe it can use your computer, or maybe it can build knowledge graphs. So there are a lot of things that matter in capabilities, but they are technical terms. So today we are going to discuss a more conceptual framework into grouping these qualities of an agent. Namely, there are 6 of them, but by no means they are like all of them. So the first one is perception, which is knowledge about the environment. Second one is decisioning, which is the quality of planning. Third one is actioning, which is the ways in which agent can action. Fourth one is agency, which is autonomy of an agent. Fifth, adaptability, how it learns, the user's preferences. And the sixth one is knowledge, and knowledge is the most important one. All of these 6 capabilities are projected on the same capability dimension, minimal to advanced, and they mean a lot of different things. In the red box, you can see that a minimal perception agent could just mean a simple chatbot, whereas a basic perception agent could mean something as cursor, which has access to all your project's information. And the third one is a more advanced perception agent, which has real-time access to your environmental information. Something like Waymo comes under it. You can also think like digital twins, which is a very famous concept in manufacturing and aeronautics these days. So we have seen how agents map onto this radial chart, this hexagon. But as a user, I want my use case also to fit in the same structure as the agents. So as a user, I'm also going to use the same framework. I'm going to define these 6 measurements, and I'm going to define my complexity that I require. From my work in Goldman Sachs, I realized that this is not enough for enterprises. We need an AI governance and risk management layer as well on top of it to make even any of this usable. On the right-hand side, you can see there is like a radial chart again, which shows that the use case of a user is a very small subset of what the tool is providing. So this is not a good use case because it might mean that the tool is very complex. It might be too complex for you, or the cost might be too much. So the rule of thumb for using AI agents is that you should use it when your task is a bit complex and can only be used, explained through language, and the risks are not too much. When starting on our product Spindle, we evaluated over 150 companies in different verticals and horizontals, and we compiled a chart. So this is a very specific subset of that chart, and this shows like 2 things. First one is different industries. It is grouped by different industries, and they are at different agentic level today. The second one is that there is a lot of noise. A lot of companies are playing in different domains, and users don't know which one they should buy to solve their problems. The key points, again, are that 69% of companies are bragging. They are just agent washing people. The reality is that the 77% of them are just at level 2 in adaptability, and similar for agency. So it's quite bad. Then software reliability or system reliability engineering, SRE, is the most mature category amongst all of them, and with an average score of 3.15. And they are the ones that have included learnable agents. below I have given two examples, call zero and slipstream, which are very niche agents, but they kind of take agency and adaptability, the limitations, to the 5. So one of them is just an agent that can make phone calls on your behalf, Second one is Google Maps for agents that can talk to other agents and learn on that sense. It's really cool. So we started with the idea of Spindle with the idea that, so today we have the capability of making agents which excel on all the 6 dimensions. But the problem is that there exists no infrastructure today that can allow them to work as teammates and out of the isolation of the laptops of individual people. So that's not possible today. And that is the uncanny valley that I was talking about in the starting. And AI is growing, it's increasing, like we have reached Cursor, we have reached Copilot, and it's constantly increasing. But when thought of it as terms of a human, as terms of a teammate, there is like a lot of compliance and a lot of gaps. So that's all. Thank you.
Thank you so much. We have time for one very quick question.
Cool. I think it was perfectly explained then.
Thank you so much.
Thanks all.
Up next, we have Sinjay Liu, who is a third-year Ph.D. student in electrical and computer engineering at the University of Texas at Austin. His research focuses on developing theory and scalable algorithms for reliable, sample-efficient learning and decision-making in autonomous systems such as robots. Please join me in welcoming Sinjay.
Hello, everyone. Today I'm going to be talking about boosting reinforcement learning with imperfect data, a multi-fidelity policy gradient framework. The motivation behind this work is that online RL algorithms often require excessive interaction with a real environment or with a high-fidelity simulation, from which gathering data can be really expensive, slow, or even unsafe. But the data from those sources are most accurate. And for example, for robotics application or complex power system or molecule simulation. And meanwhile, in a lot of application domains, people have been building low-fidelity simulation tools, such as reduced order models, generative world models, heuristic reward functions, or digital twins. And gathering data from those sources is actually very cheap, fast, and also safe. However, the main challenge is that those data sources are often biased. So we have a fundamental mismatch here. And in this research project, we look at the research problem of how can we enable sample-efficient reinforcement learning in the real environment by mixing multi-fidelity data while being robust to low-fidelity data biases. And namely, how do we build a blender in the middle? And we look at this problem through the lens of on-policy policy gradient algorithms. So these algorithms sample trajectories from the environment and try to estimate a policy gradient using the sample trajectory and by averaging over the sample trajectories. And I put a generic notation here. This x is some random variable, which is the per trajectory policy loss, and different on-policy algorithms use different expressions for this quantity, but they are same in spirit. And the main challenge is, okay, so we have limited access to high-fidelity samples. We can only sample very scarce high-fidelity samples and try to estimate that quantity. So therefore, the estimator is inevitably high variance, and also which causes slow convergence of those algorithms. And the strategy we take in this work is to ground the learning in the high-fidelity samples, meaning that we build an unbiased estimator while using abundant low-fidelity samples to reduce the estimator variance. Our contribution is MFPG in short, where we sample multi-fidelity data and compute a multi-fidelity policy gradient estimator. So it works like this. So first we sample pairwise correlated trajectory samples, a very small amount, and use those samples to compute the high and low fidelity random variables respectively. And then additionally, we gather cheap, abundant low fidelity simulation data in order to estimate the mean for the low fidelity quantity only. And therefore, we combine the two sources of data to construct a so-called control variate policy gradient estimator. And the rest of this procedure just follows exactly like standard on-policy policy gradient algorithms. And we differentiate through the laws, apply policy gradient to update the policy, and then iterate. So this framework is generic, and we can instantiate this framework by different policy gradient algorithms by defining that random variable acts differently. And in this work, we use reinforce in order to establish a clean convergence analysis. And so the multi-fidelity control variable estimator I presented earlier has two important features. One is it's unbiased with respect to the high fidelity samples, high fidelity environment, and it has reduced the variance by a factor of 1 minus rho square, where rho is the Pearson correlation between the high and low fidelity random variables. And therefore, we can establish that MFPG accelerates the convergence for the reinforced algorithm. And the bottom line is simple. So the better the low fidelity data quality is, so the better it matches the real world. And the higher the correlation is, and therefore the lower the variance is, so we have faster convergence. And finally, a few quick experimental takeaways. So in our experiments, we find that MFPG handles both dynamic gaps and reward misspecification. It actually even works when the low fidelity environment is anti-correlated adversarially. And also, because MFPG is unbiased, which is different from existing methods, and MFPG shows the strongest consistency and robustness to low fidelity data biases compared to the off-dynamics baselines that we compared. And to summarize, MFPG is a sample efficient reinforcement learning framework by mixing scarce high-fidelity data with abundant low-fidelity data. And it is unbiased with respect to the high fidelity and has reduced variance. And also, it is robust to low-fidelity data biases. And finally, huge thanks to my team. And if you want to know more details, here's the QR code to our website. Also, you're welcome to join our poster session later. Thank you.
And last but not least, our next speaker is Albert. He is in his final PhD year here at UT Austin. He works on interesting ways to leverage natural language information to help real-world robots do more and learn faster. Please join me in welcoming Albert.
Imagine preparing for a dinner party with a friend. You might collaborate with your friend, for example, by cooking, while asking your friend to make drinks. So you would allocate tasks by skill set. Now later, your friend might ask you to wash dishes, but if you're busy vacuuming the floor, your friend would have to adapt to your availability and willingness to help. Imagine a robot in place of your friend. Today's robots struggle on long horizon complex tasks, so they must collaborate and communicate with humans to see who is best suited to perform each step. Our key hypothesis is that a collaborative robot must leverage both agents' physical capabilities and adapt to changing human preferences and helpfulness through bidirectional communication. So there is prior work where humans are initiating most of the conversational threads, such as chatbots, and the robot is mostly responding, or the other way around, robot-initiated dialogue. And these are single initiative dialogue frameworks which offer very limited adaptability for collaboration. There is mixed initiative dialogue research starting from 1970, but these works have not been proven on physical robots. So we introduced MikoBot, Mixed Initiative Collaborative Robot, which is to apply mixed initiative dialogue for the real-world human-robot collaborative setting. MikoBot makes decisions at 3 key levels to operate with a human collaborator in the real world: the meta planner, the iterative planner, and the action executor. The meta planner processes the world state as well as the dialogue history to produce adaptive planning code. The iterative planner estimates the human's likeliness to help the robot, as well as quantifies the robot's capabilities through Q functions learned in simulation. And it executes the meta planner's code to produce the most likely allocation between agents for allocating the rest of the tasks. With this best allocation in hand, the action executor decides whether the robot should execute a verbal action, which is the exact words to tell the human, or a physical action, which is a sequence of arm and base joint commands to effect change in the world. So MikoBot outputs either physical actions that affect the world state or verbal actions that are perceived by the human, who also perceives the world state to act physically in the world. Here it is in action. And so the human is doing their own work on their laptop, and the robot is working autonomously.
You will put the car into the box later, right?
Absolutely. I will be happy to put the car into the box later.
How many of you like the robot voice?
Could you please seal the box? Thank you.
If you bring me the ribbons, I can then wrap the ribbons around the box.
Sure, I can bring the ribbons to the coffee table and you can use them to wrap the ribbons around the box. Could you please cover the box with the lid? Thanks so much.
Sure, I'm happy to.
Can you please wrap the ribbons around the box? Thank you.
Of course, I can do that now. Thanks for bringing the ribbons earlier.
Can you decorate the box? Thanks so much.
I don't want to do it right now. I'm busy. I want you to do it.
How about we split this task? You can cut a piece of tape and put it on the box, and then I will put the bow on the box.
All right, I guess I can do that part.
Could you cut a piece of tape and put it on the box? Thanks.
Yes, doing that now.
All right, so that was one. I guess we have results on 18 unique human participants, and you just saw one of the users. And we have 3 tasks. So the y-axis is a success rate, and the x-axis is a percentage of the steps that were done by the human. And the gold star is an ideal robot, which is not naggy at all, and it achieves perfect success and no human effort. But we're in the real world, so our robot achieves 0% success if it's working alone. So if there's no human help, it does not succeed at all, but it achieves like a 40% partial step completion rate. If we use an LLM baseline, that achieves higher partial success, which is a hollow circle, as well as full success, which is a colored in circle. And our method achieves 77% success, around 94% step completion rate. And so we believe our method most effectively leverages human effort toward improving task success. So, in conclusion, MikoBot is the first work to enable mixed initiative dialogue for real-world human-robot collaboration, and we showed that mixed initiative dialogue improves collaborative manipulation outcomes compared to, and adaptiveness to the human collaborator compared to single initiative dialogue. Thank you very much.
Thank you so much, Albert. Is that a quick question? Yes. Okay.
What was stopping the robot in that video from just going towards the couch, pushing the table into the subject?
There are 2 LiDAR sensors on the robot's face, and there's a map that the robot is localized within, so it's not going to crash into things.